All right, welcome to the Explainer. We're surrounded by computers all day, every day. But have you ever really stopped to think about what's going on deep inside them? You know, under all the apps and websites, there's this secret language at work. And the crazy part is it's spoken with just two symbols. You've heard it a million times, right? Everything a computer does is just ones and zeros. We call it binary code. But why? Why would our most powerful, most advanced machines be built on a language that seems so, well, basic? The answer, it turns out, is surprisingly simple, and it has everything to do with the physical world.
So, to really get this, we have to forget about the software for a minute. We need to get physical and look at the actual hardware, the real nuts and bolts inside the machine.
Because at the very, very bottom of it all, every single thing your computer does, from sending an email to rendering a blockbuster movie, it all boils down to controlling billions, literally billions of tiny, microscopic switches.
And that tiny little switch is called a transistor. Now here's the key thing to understand about it. It's incredibly simple. A transistor doesn't have a middle ground. It can't be kinda on or a little bit off. It can only exist in one of two states. Either electricity is flowing through it, or it's not. It's either on or it's off. That's it.
And this is the light bulb moment. This is where it all connects. The pioneers of computing needed a way to represent those two physical states, so they made a brilliant, simple choice. The off state with no electricity would be represented by the symbol 0, and the on state with electricity flowing would be 1. That's the fundamental link between the physical world of circuits and the abstract world of data. And you know, this system is incredibly reliable. A clear on or a clear off means there's almost no room for error. It's the perfect, simple foundation to build on.
So, okay, we've got two symbols, 0 and 1, representing two states, off and on. But how in the world do you get from what is essentially a light switch to representing every number, word, and photo we've ever seen?
Well, the answer is a counting system called binary, and honestly, it's not as strange as it might look. It works on the exact same principles as the decimal system we all use every day. You know, our system has 10 symbols, 0 through 9, so we call it base 10. Binary is a base 2 system, which just means it only has two symbols to work with, 0 and 1.
Let's just look at this side by side. On the left are familiar decimal numbers. On the right, they're binary twins. Now 0 is 0, and 1 is 1. Easy enough, right? But things get interesting when we need to represent the number 2.
See, in binary, once you've used 0 and 1, you're fresh out of symbols. So you do the exact same thing we do in our system when we run out of digits at 9, you add a new column to the left, and you reset the first one back to 0. So the number 2 becomes 1, 0. The number 3 is 1, 1. And to get to 4, we're out of symbols again, so we carry the 1 over, and it becomes 1, 0, 0.
You know how in our everyday numbers we have the ones place, the tens place, the hundreds place, and so on? Well, binary does the exact same thing. But instead of being based on powers of 10, it's all based on powers of 2. So you have the ones place, then the twos place, the fours place, the eights place, and on and on. By just turning these different switches on or off in a sequence, you can build literally any number you can think of.
Okay, so computers can count using nothing but on-off switches. That's a huge leap. But how do we organize all this to represent something more complex, like, language? This is where we get two of the most famous words in all of computing. Each one of those individual switches, each 1 or 0, is called a bit. It's just a little mashup of the words binary digit. And to keep things organized, computers like to group these bits into little packages of 8. And that package, that's what we call a byte.
So why 8? What's so special about that number? Well, if you have 8 bits, and each one can be either on or off, it turns out you have exactly 256 unique combinations you can make. That gives us a vocabulary of 256 different words to play with, starting from all zeros, all the way up to all ones.
And that brings us to the next big question. A computer sees a pattern of 8 switches, a byte, and it understands it as a number between 0 and 255. But how does it know that we want to see that exact same pattern as, say, the letter A?
Well, the simple answer is, we told it how. We gave it a universal secret decoder ring. It's called ASCII, and it's basically just a big chart, a universal rule book that assigns one of those 256 numbers to every single uppercase letter, lowercase letter, number, and punctuation mark you can shape.
So for example, the ASCII standard says, hey, The number 65, that's always going to be an uppercase A. It's a rule. So when you hit the A key, your computer sets a byte to the binary pattern for 65. Then the software on your computer reads that number, looks it up on the ASCII chart and says, ah, that's an A, and puts it on your screen. Simple as that.
All right, let's push this even further. We've gone from switches to numbers to text. But what about the really complex stuff we see every day on our screens? How on earth can a simple on or off system create a rich, detailed photograph?
So here's the trick. When you look at a digital photo, you're not actually seeing one continuous image. What you're really looking at is a giant grid made up of thousands or even millions of tiny, single-colored dots. And we call those dots pixels.
This side-by-side view really shows you what's going on. On the right, you can see the individual pixels. Each one is just a solid block of color. But when you pack millions of them together and see them from a normal distance, like the image on the left, your brain does the rest and blends them all together into a smooth, clear picture.
So how does the computer know what color to make each one of those tiny squares? Well, surprise, surprise, it's just numbers again. The color of every single pixel is stored as a set of values. Usually it's 3 numbers, one that tells it how much red, one for how much green, and one for how much blue to mix together to create that exact shade.
And the more bits or the more information we use for each pixel, the more colors we can show. But there's a trade-off. A simple black and white picture only needs 1 bit per pixel. It's either on or off. But to get what we call true color, you need 24 bits for every single pixel to store all that rich red, green, and blue data. And as you can see, that makes the file size way, way bigger.
And this is where it all comes full circle. Every one of those numbers, representing every shade of red, green, and blue for every single pixel in that photo is, you guessed it, just another long string of ones and zeros. It all comes back to those billions of tiny switches being either on or off. It's kind of mind-blowing when you really think about it. From the simplest possible thing you can imagine, a switch that's either on or off, we've managed to build the entire, infinitely complex digital world that we live in today. It's all just layers upon layers, built on that incredibly simple foundation.
You know, this whole digital revolution happened because we figured out how to use an electron to flip a tiny switch. It really makes you wonder, what's next? Things like quantum computing are already trying to use the state of an atom as their switch. What do you think will be the next simple, binary choice that unlocks a whole new world of complexity?